The component in this diagram is called a thermistor. Thermistor. It has a property that for when temperature changes, the resistance change a lot. So for example, we can warm this gently, either by putting a warm object near it, maybe not a fire, but maybe some warm water to heat it up, just between 0 and 100 degrees Celsius, and see what happens when we measure the current. So let's say the battery has a voltage of let's say 1.5 volts, and suppose that we have an ammeter to measure the current. What we'll find is that as we heat the thermistor, depending on the type of thermistor, but for example, one thing that could happen is that when we heat the thermistor, the current decreases because, let's see, when we heat the thermistor, the current increases, because the resistance of the thermistor drops. So for example, if I think of measuring the temperature, let's say the temperature in degrees Celsius. Let's say I measure the temperature in degrees Celsius and measure the current as I warm up the thermistor, and then plot the graph. Let's take a look at what the graph might look like. Okay, that's the temperature, that's the current. So let's say the temperature is in degrees Celsius, and we are measuring it between 0 and 100 degrees Celsius. And what could happen is that when this is at 0 degrees Celsius, we might have let's see, a small current of let's say 0.001 5 of an ampere. Okay, and as we warm up the thermistor, as the temperature increases towards 100 degrees Celsius, you would find that when we measure the current, that the current increases until when it reaches, temperature reaches 100 degrees Celsius, the current might go up to say 1.5 ampere. Right, that's probably too large for a normal battery, but well, I'm just using this as an example. So let's say at 100 degrees Celsius, the ammeter measures a current of 1.5 amperes. So if I plot these 2 points at 0, at 0 degrees Celsius, I'll get a point here. At 100 degrees Celsius, I'll get a point there. So I can imagine in between, as I increase the temperature, I write down the values of the temperatures at maybe 10 degree interval and the current at those points. So so that I can plot a graph. So I might get a graph that looks like this, with the current increasing as I heat, as I warm up the thermistor. Okay, so I'll get a graph that is increasing, and this shows that the thermistor resistance drops as temperature goes up. Now let's think about the resistance. Think about what the resistance might be. Recall the formula. Let's recall the formula for resistance. It's resistance is equal to voltage over current. Okay. So if I want to find the resistance here at this point, I would take voltage over current. Voltage is 1.5 volts. So 1.5 over 1.5. 1.5 over 1.5 gives 1 ohm. So I might have a resistance of 1 ohm at 100 degrees Celsius. But at 0 degrees Celsius, okay, the voltage is still 1.5 volts. The current dropped to 0.015. If I now divide this, my answer is 100 ohms. Okay. So there is this unusual behavior. But what kind of a material can give such a behavior? Now let me just write down an example. If you Google for thermistor, you will find some information in Wikipedia. And an example of a thermistor material might be something called, as an example, something called iron oxide. Iron oxide. The precise chemical name is iron 3 oxide. And with some tiny amount of impurity of titanium, tiny amounts of titanium, and we would not go into the details of how this works, but I'll just say very briefly that for a thermistor of this material, it has this unusual property because this material is acts as a semiconductor. Now, a semiconductor, you can think of it as essentially a material with very small amounts of conducting electrons. Unlike copper, unlike metals, which conducts very well, semiconductor has only a very small amount of conducting electron, and but it can actually gain more conducting electron if the temperature increases. Right? If the temperature increases, it will actually gain more conducting electron, and that helps to make it more conducting. Which is why, in this case, as the temperature increases, the resistance can actually drop. Right, so we learn more about semiconductors in a much later video. So for now, that's just to give an idea of the kind of material that would produce such a behavior. So having had an idea of how the current could change with temperature, the other thing we should look at is a graph of the resistance against temperature. So if I want to sketch or plot a graph of the resistance against temperature, let's see what that would look like. So the resistance, the unit of resistance is ohms, and I'm going to use degrees Celsius again for temperature. So temperature range that I'm using here goes from 0 to 100. 0 to 100. And if I start by plotting the resistance, say at 0 degrees Celsius, resistance there is 100 ohms. So that's up here, 100. So I have a point there. And at 100 degrees Celsius, the resistance is 1 ohm. So that would be all the way down here, very low, much lower resistance, and I get another point down here. And in between, a typical graph, resistance against temperature graph of this type of thermistor might look like this, right? You might get a curve. And we can find the resistance in the points, for the points in between, just by doing a similar calculation using Ohm's law for all these points in between that we have measured of the current and using the voltage of the across the thermistor. So this is the kind of graph that we would expect, a kind of curve that where showing that the resistance drops quickly, but usually not in a straight line, in some kind of a curve. But what is the point of a resistor? What is the purpose of a thermistor? Thermistors are useful as a way to detect temperature. For example, if there are electronic circuits that could be used to either measure temperatures or to more commonly as a device to trigger, to make something happen, to do something if the temperature either gets too big or too small. An example might be if you have ever looked inside the cover of say an air conditioning unit, you might find a thermistor that looks exactly like that. What it does is that if when the air conditioner gets too cold, right, the resistance of this increases, and the electronics in the air conditioner can then shut down the air conditioner or just stop it until the temperature warms up again before it starts blowing the cold air. So that's one way a thermistor can be used. Another way might be as part of a fire alarm. If there's a fire, things gets too hot, the resistance drops, and that could also be used as part of a electronic device to trigger a fire alarm, for example. Another thing that I should mention is that a thermistor, as I've described it, is something for which the resistance changes a lot when over a certain temperature range. Now, if you remember previous video which describes, for example, the resistance of a filament lamp, we have seen that the tungsten filament, as the temperature increases, the resistance also changes. But in that case, compared to this thermistor, the resistance increase. The resistance of a tungsten filament lamp only increases by about 10 times when the temperature increases all the way from room temperature to 3000 degrees Celsius. So compared to a thermistor, the change in resistance in a thermistor would be much bigger over a small temperature range. And such a big change is important if we want it to be quite sensitive to the temperature when we use it in electronic devices.